from the Liberty University and exploration of reduced order modeling for wave-induced transonic atomization.
Today I'm going to be talking about the same system that Femi was talking about, the wave-induced atomizer. So, motivation for this talk, atomizing non-Newtonian fluids is difficult and very useful. So in this case, the atomizer we're focusing on, high gas-liquid ratios lead to more disintegration, more breakup. That's nice. That also means it's a low-efficiency atomizer, though. So we're trying to make a low gas-liquid ratio atomizer. Enter the wave atomizer, which is wave-augmented varicose explosions atomizer. This is a step-by-step view of a 3D cycle of it, where you see that it bursts out a very, very complicated 3D pattern. A lot of simulation time goes into this. If you see here, we have 5 different points that are of interest in this atomizer. This talk will be focusing on the exit point. This right now is a 2D slice of the 3D simulation. And this is another 2D slice of the 3D animation, well, an animation of a 2D slice of the model. As you see it playing out, you'll see the behavior where it pulses out into the center, is pushed out by the steam with particles breaking off in the process, and then it bursts outward again with more particle breakup right there. And here's another image of that instead, just step by step. So, continuing our motivation, that was context. I worked on an axisymmetric and a planar simplification of this. So, as mentioned, it's expensive to run. 2D, not nearly as much. If we can get anything good, that's already a win. We're not expecting to get the complicated 3D behavior that you see outside the nozzle. Droplet breakup is a very 3D effect. Anyways, you can't really get atomization in 2D and expect to represent it that well. So I was running it on ANSYS Fluence 2022 release 2, UIC-VOF, approximately 20-8 time steps. And both the 3D model that we were comparing it to and the 2D models I was using, they were both initial refinements, proof of concept. That's why it was such low resolution animations. Everything was focusing on the exit point, be it for the 2D model or from the 3D model. In the case of the 3D model, we do take multiple exit points at different angles, but they're all at the same point relative to the atomizer. The remaining reason for that is once you get past there, it's going to be highly 3D behavior. This is the last point in the atomizer's flow that we would actually expect somewhat 2D behavior that could be comparable to what the simulation would provide from the simplified one. Once again, this is the point designation image. Just to give context, that is the exit point. That is what the rest of this will be focusing on, be it for 3D or for 2D. So here is an animation of the 2D model, specifically an axisymmetric one that should be much more analogous than the one that I'll show you in a second. And just looking at it in general, sorry about that. It's got the same general behavior as a 3D model, so that qualitatively might be useful, but it's not much to go off of yet. Similarly, we have a 2D planar model, and this one also behaves similarly, so that doesn't tell us too much. The planar model we constructed by adjusting the mass flow rates in the 2 inlets. These were adjusted so that it would be the same ratio of mass flow rate to area that it was flowing through in the 2D planar or in the 2D axisymmetric. This is what the raw data looks like that's not very useful. So we're going to be doing cumulative time averages. For cumulative time average, we just define a certain amount of data that we want to focus on, and at the beginning, we just average it from time, just define time 0, average it from time 0 to time n. That is what you have for data point n. Then from n plus 1, you average from time 0 to n plus 1, and so on and so forth. We're comparing the 2D axisymmetric, the 2D planar, and the 3D average, which we got from averaging 5 different exit points throughout that 3D model. We will be focusing on the velocity magnitude, the volume fraction of sludge, the turbulent kinetic energy, the strain rate, and the specific dissipation rate at that exit point. Time will be measured in wave times instead of raw convective time, as you saw in the previous graph. So there's about 1,000 wave times per second. We're going to be focusing on 70 wave times on the graph. So here you see the velocity magnitude cumulative time average plot. Note that blue is the 2D axisymmetric, red is the 2D planar, and green is the 3D average. Those colors will stay consistent through the rest. If there is more, they will still be those 3. So we have at least similar order of magnitude behavior, and they're pulsing in a similar way, but that's only going to tell us so much right now. We see the 2D axisymmetric is higher than the 2D planar, but the 3D average is in the middle. If we go to the next slide, we can look at the volume fraction of sludge. And here, 2D axisymmetric is once again higher than 2D planar, but not the 3D average. And we're going to have jumping around. The 3D average is sometimes higher than the 2D average, sometimes lower, but the 2D average is always higher than the 2D planar, and the 2D planar never higher than the 3D average. So we've seen the strain rate, now the specific dissipation rate. Now we're going to look at the fast Fourier transform of those same variables. Because the data sets are different sizes, the magnitudes will be quite the range to them. So we won't care about that. The other thing to note is that the individual points in the 3D model, slightly different frequency than the average points, but it never varied by a significant amount. So here's one chart of all the points together. That's very messy, but it's to show you that the green one is just slightly to the left of all the individual components of the 3D. The rest of these, after the velocity magnitude, we're going to focus on just the 3 main points that we care about: 2D average, 2D planar, and 3D average. So we go to the volume fraction plot. Like the previous one, we see the 2D planar is below the 2D average, which is below the 3D average. We're going to see this pattern hold out through most of it. When we get to strain rate, once again, 3D average is the highest, 2D average is a little bit lower, 2D planar is below that. Almost the same graph on omega for specific dissipation rate. So, just to recover what our findings were here. Cumulative time average, 2D axisymmetric is always greater than 2D planar for these values, and 2D planar is never greater than 3D average. For the fast Fourier transform, 2D average is always a greater frequency than the 2D planar, and it's always closer to the 3D average than the 2D planar is, which that was not the case in the cumulative time average. So in conclusion, we can get something of an approximation of the 3D, which could speed up the design process for the atomizer if we want to consider different geometries. Axisymmetric was more accurate than planar. That's good. It'd be a bit odd if that wasn't the case. However, we need to test these at higher resolutions and at different geometries if we want to know that this will actually continue to be useful. Thank you.